Hello, we're going to look at an interesting topic today called invariant points and lines. We're probably going to do this in two parts. See how it goes. Invariant points and lines are points and lines which, under some kind of transformation, of course we've seen some transformations now, we've seen reflections, rotations, shears, enlargements, a variety of rotations and whatevers. And under these transformations, sometimes there are certain points that don't move. So this point here, for instance, now this is meant to be a reflection in the line y equals x. So if I reflect this curve in the line y equals x, you can imagine what happens. It broadly looks like this. And that goes roughly there, I think. So I'm just trying to do it relatively accurately. And then something like that. But you'll notice wherever the point on the line is on the line, so for instance there it doesn't, but there it doesn't, there, but this point is on the line, so as whenever a part of the curve crosses this line y equals x, obviously I'm reflecting the line y equals x, so it's got nowhere to go, it stays where it is, and that's no big surprise. These points are called invariant points, points that under some transformation don't change. So this idea of invariance is where you do something to it, but there's no change either to the whole thing, or it might be that there's certain points which are invariant, or lines that are invariant. So invariant points, transformations often leave some points unmoved. In other words, a point doesn't move as a result of some kind of transformation. These are called invariant points, invariants. So there's loads. So I've got one here, I've made one up, but you'll notice 6 2s are 12. Take away the 10 you get from this one gives me 2 still. Notice the 2 is still a 2. And 2 2s are 4, but then plus and minus 6 is still minus 2. So whatever this thing does, I've no idea what it does, to be quite honest. 2 minus 2 stays at 2 minus 2. So that coordinate doesn't move. It's called an invariant point. It's an invariant point. And this is the words you've got to use to describe a point that doesn't ever move. So to find an invariant point, I kind of do what I've just done. I basically say I've got some matrix, which presumably I'll get told. And I'm going to times it by xy, but my answer's got to be xy. Notice the point hasn't changed. So we're going to have a look at a question like this. It says, look, I've got a matrix, and it says 3 minus 2, 2 minus 1, and I want to find the point where this becomes an invariant point. And it reckons determine whether there are any lines in invariant points. Well, let's first of all work out if I can find a point first of all. So I'm going to say xy, a bit like we did before, and when you do it we're going to get xy. Well, let's multiply this out. I get 3x minus 2y, and that equals top answer, which is x. And I've got 2x minus y, and that equals y. Let's play around with these two equations basically. That way I can see that 3x and that x are going to join together, so I'll get 2x minus 2y equals 0. Well, actually that simplifies, isn't it? You can imagine that saying 2x equals 2y. Or probably better just to write y equals x. You usually put the y first in a situation like that. It could be x equals y, I suppose. So what's this happening? Well, that moves over. That's what they're on about. Look at this. 2x equals 2y again. And 2x equals 2y means that y equals x again. So in actual fact, I tried to find a single point where it worked for, and it actually came up with an equation. It basically said any point on the line y equals x will be invariant under this matrix. So it doesn't matter what it is. So for instance, 4, 4 will work. But so will minus 22, minus 22. As long as the y equals the x, these points won't move. Let's test that out. I picked 4, 4. So let's test that out. 3 minus 2, 2 minus 1. I'm picking up 4 and 4. I'm pleased I didn't pick 22s because I would have had to have done some proper maths. 3 4s are 12. Minus 2 times 4 is minus 8. Yeah, that gives me 4, doesn't it? 12 minus 8 is 4. 2 4s are 8 minus 4. Yeah, that gives me 4 as well. So yeah, it worked. So as an answer to this question, it says y equals x is the line of invariant points for the matrix. Probably worth writing all that down. That's the posh way of saying that y equals x is the line of invariant points. So here's another one. It says example. It says show that it's got only one invariant point. Oh right, so I do the same trick though. I don't know what that point's going to be. I'm going to chuck x and y into this. And it reckons this time there'll only be one. So I set it equal to x, y again. Multiply this out. Minus 4x plus the y equals the x. 3x minus 2y. So multiplying out matrices becomes really important, doesn't it? And I do the same thing, I suppose. I'll tidy them up. Last time when I tidied up, I ended up with the same equation. But maybe I won't this time. Move that over. It becomes minus 5x plus y equals 0. Or I suppose I could write that as y equals 5x. This time, look at this. This time it's different. Move that over there. I get 3x equals 3y. So now I get y equals x. So notice I've got two different equations. And because I get two different equations, there's not one line that works. It just, when do these two things when are these both true? Well, when y equals this and y equals that, you can just, it's simultaneous equations, you set them equal to each other. 5x equals x. Well, move that over. 4x equals 0. It becomes a minus 1, move that over. Oh, so x equals 0. So that's interesting. X is 0 at one point. And notice y equals x or y equals 5x will both give the same thing for y. If x is 0, then y is 0 as well. So I think the obvious answer here is that 0, 0 is the only invariant point. So let's see if we agree. Solution 0, 0 is the only invariant point. Other invariant lines. So there are, however, other lines that can be described as being invariant. And this is an example of that, perhaps. So you'll notice here I've got a y equals 2x, and I am perhaps trying to reflect points in this line, or it doesn't even seem to be, oh no, it is a reflection, isn't it? So this point seems to reflect over here. Okay, yeah, I agree with that. And this point seems to reflect over here. So you can see that even though they're not reflecting to the same point, they are staying on the same line. And that's the weird thing about this question. So on this question, we're just saying to ourselves, I don't know what this line is, it doesn't tell me. But this would be described as an invariant line. Invariant line. Not in quite the same way as before, but it's still an invariant line. Here you can see that any point on the blue line stays on the blue line. Note that the point doesn't stay in the same place, but it does stay on the same line. So sometimes there are only a few such invariant lines for a transformation, whereas in this case there are infinitely many such lines. That's basically saying I could have chosen this line over here instead. You can see there's another line. And all the rule would be on this case, as long as it's right angled to the y equals 2x line, it will be an invariant line. So we'll perhaps see a few of those in what's coming up, and perhaps not. I don't know how much of that will start. Now, all I want you to do initially is just to have a look at these questions. I've said don't do question 2, but we'll see how far we get through them. And then we'll do this again in another lesson. And hopefully between the two lessons we'll understand everything that we need to understand. So that we'll call it quits for this one, a relatively short video, and we'll see what we can come up with in class.